At the end of the last video, we had just looked through this process that you see here on the screen for finding zeros of a polynomial function. We're actually going to implement that in this video. Here's an example. So the first step above is to use the rational zeros theorem to find the possible rational zeros. Actually, the first step really is, can you factor it using some other technique that might be easier or more straightforward that you previously knew? I look at this, and when I see four terms, I think maybe factoring by grouping. But factoring by grouping will not work here, because when I factor the x squared out of the first two terms, it's going to leave x plus 3, and the GCF of this negative 11x minus 5 being negative 1 would be 11x plus 5 left in there when you take the negative out, and that doesn't match the x plus 3. So if they don't match, factoring by grouping doesn't work. We are going to try to find the possible rational zeros, right? So remember, we have our p, which would be divisors of the constant, which is negative 5 here. That's just positive or negative 1 and positive or negative 5, since 5 is prime. Q would be divisors of the leading coefficient, which is 1, so plus or minus 1. So our possible rational zeros are, we put the 1 over the 1, we get 1. We put the 5 over the 1, we get 5. And of course, any combination of those will give both positive and negative. We have four possibilities to try. There is no reason to try and see if 2 is a zero of this polynomial. It won't be, based on the rational zeros theorem. Let's start with, 1. We're going to use synthetic division. We got our coefficients, 1, 3, negative 11, and negative 5. The biggest thing with synthetic division is make sure that you don't miss, and if there are any missing terms, you got to put a 0 in place of them, because we're not leaving the variables to help us. So the whole point of this is we don't have to keep carrying those variables down. We bring the 1 straight down, then we multiply 1 times 1 and put it there. Then we add 1 times 4 and put it there. Add negative 7 times 1 goes there as negative 7, and we get negative 12. That remainder is not 0, which tells us x equals 1 is not a zero of f of x. If you plugged in 1 into this, you would get negative 12, actually, whatever that remainder is. Remember the remainder theorem. Okay, we have 3 other possibilities. Let's try negative 1. Our coefficients there. The 1 comes straight down, then we multiply. Negative 1 times 1 is negative 1. Add gives us 2. Negative 1 times 2 is negative 2. Add there, we get negative 13. Negative 1 times negative 13 is positive 13. That gives us 8. Not equal to 0, so that one didn't work either. Let's try 5. 1, 3, negative 11, and negative 5 are the coefficients. The 1 comes straight down. 1 times 5 goes here. It's 8. We multiply those, we get 40. Add those, we get 29. 5 times 9 is like what? Well, 5 times 30 would be 150, so 145. Add those, you get 140. Not 0. That doesn't work. I'm a really bad guesser, aren't I? Negative 5 is the only other possibility. Bring the 1 down, multiply, we get negative 5. Add those, we get negative 2. Now we add. We multiply negative 5 times negative 2 to get 10. We add, that's negative 1. Negative 5 times negative 1 is 5. Add there, we get 0. Yay! That's what we're looking for, a remainder of 0. And I didn't really write it up here, but these not being 0 tell us that x equals negative 1 is not a 0. And x equals 5 is not a 0. But x equals negative 5, because the remainder is 0, tells us x equals negative 5 is a 0. It also tells us from our previous theorems that x minus negative 5 or x plus 5 is a factor of f of x. And specifically, f of x can be rewritten as x plus 5 times x squared minus 2x minus 1. That x squared minus 2x minus 1 comes from these numbers here are the coefficients on the other factor. So this is the x squared, the x, and the constant term. Sometimes people will work backwards, like constant x, x squared, and then keep going up. I like to think of it as if I'm going to get an x cubed, because I started with an x cubed, right? I took out an x, I'm going to have one degree less than that. So either way, if there's a missing term, you should have a 0 in that bottom row. The question, let's go back and make sure we're answering the question here. The question is actually find all the zeros of that and factor it into linear terms. We don't have linear terms yet. We have one linear term, the x plus 5, and one quadratic term. We need to factor further and find the zeros of that. The first thing I try is just regular factoring of a quadratic. There are no two numbers that multiply to give me negative 1 that add up to negative 2. So negative 1, our only possibilities are negative 1 and positive 1. Those don't add up to negative 2. So we also know, because our possible rational zeros there, none of the other ones worked, that that's not going to factor nicely. So we're going to use the quadratic formula on x squared minus 2x minus 1 equaling 0 to find out what that the other two zeros are. X will equal the opposite of b will be 2 plus or minus the square root of negative 2 squared minus 4 times a is 1 and c is negative 1 all over 2 times 1. And that will equal 2 plus or minus the square root of, let's see, we get 4 plus 4, so that's 8 all over 2. That will simplify to 2 plus or minus 2 root 2 all over 2, which is 1 plus or minus the square root of 2. So that means our zeros of f of x are, we got negative 5, x equals negative 5, x equals 1 plus the square root of 2, and x equals 1 minus the square root of 2. As far as factoring it into linear factors, that's basically saying, how do I break down that quadratic? F of x will be that x plus 5, and then it's always x minus the 0. So it'll be x minus 1 plus root 2. Then another factor is x minus 1 minus root 2. So it's the 3 of those factors. We don't typically see factors like these last two. It would be much more common to say it is factored in this form here. since it doesn't factor into rational numbers there. But this specifically asked us to factor it into linear factors, and linear factors, or linear terms, should really say factors, not terms. Linear factors are where you have your degree is 1 on each of the factors. So x minus some number. Let's try it again. This one's bigger. So let's try this one. It's already in descending order, so that helps me. The first thing I do notice, though, is that I do want to pull an x out of this. I have a GCF of x here. And then I'm going to work on factoring this part here further using our new techniques, because I don't have any other techniques for factoring something that big. Let's try our rational zeros theorem. So P would be divisors of 12, which would be plus or minus 1, plus or minus 2 divides that evenly, 3 divides it evenly, 4 divides it evenly, and 6 would divide it evenly, and 12 divided evenly. Ooh, that's a lot. Q will be divisors of 3. Remember, we're going to keep that x there, but we're focusing on trying to further factor this polynomial of degree 4. Plus or minus 1 and plus or minus 3. So my possible rational zeros here, all of those over 1 are going to give me that first line. The p's will always be in your list of possible rational zeros because you'll always have 1 in the q's. Remember, you're looking at p over q. And then we have to put each of these over 3. So 1/3, 2/3, 3/3 would be 1, which we already have, so we don't need to do that. 4/3, 6/3 would be 2, and 12/3 would be 4. So that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we actually have 18 possible rational zeros. Phew, that's a big list. Let's hope we get a hit before we get to number 18. Let's try one. And I'm going to focus exclusively on this after the x is pulled out. 3, 2, negative 25, negative 28, and 12. You always want to pull that GCF out first. 3 comes straight down. We multiply 1 times 3. Put it in that spot, add, we get 5. 1 times 5 is 5, add, we get negative 20. 1 times negative 20 is negative 20, which gives me negative 48. When I multiply those, I get negative 48, and I add, I get negative 36. Not 0, x equals 1 is not a 0 of f of x. What I notice is these numbers getting quite negative here. It makes me wonder if a negative number might work better to keep these numbers closer to 0, so that you're adding like possibly some, bigger positive numbers. We'll see. We'll see what happens here. 3 comes straight down. We multiply. That gives us negative 1. Here is positive 1. When I multiply negative 1 times negative 1, I add. I get 24. That gives me a negative 4 when I add, a positive 4, and so I get a 16. Not 0, but I like it better because this number towards the end here was a little better. Let's try a 2. Maybe I'll try a negative 2. Because I liked how that negative, I just liked how it felt a little bit better. I didn't like how these negatives were getting so big with that positive one. Negative 6, when I multiply, I add, that's 8, 17, negative 34. That gives me, nope, they're both negative. That's really negative. Negative 62, that's not going to work. 124, not 0. It doesn't really matter what the number is, right? Just noticed, I think I made a mistake here. Negative 25 plus 8 would be negative 17. When I multiply those, that would make this a positive number. And that's going to make this a 6, which makes this a negative 12. Yay, that's good. All right, so x equals negative 2 does work. When you get remainder 0, x equals negative 2 is a 0 of, is this f of x? Did I call it f of x or g of x? Yep, f of x. So here's where we are so far. That also means x plus 2 is a factor. So f of x, remember we had that x hanging out there. We just figured out that x plus 2 is a factor, and now I'm going to use these numbers as my coefficients on the other remaining factor. 3x, constant x squared, x cubed. 3x cubed minus 4x squared minus 17x plus 6. Okay, don't forget that x that we originally factored out. That's where that came from. Okay, now we need to repeat process for 3x cubed minus 4x squared minus 17x plus 6. The good news of this is that doing this will potentially narrow down your list of possible rational zeros. It definitely will not add to it, because if it didn't work in the original, it can't work now. And the same thing is true for the actual zeros. So if x equals 1 and x equals negative 1 did not work in this polynomial, then they can't work in this cubic polynomial, because it would have worked above if that was a factor. If x minus 1 was a factor, it doesn't matter what order you get these factors in, right? It couldn't have not worked above and worked now. One thing we do have to remember, though, is that the negative 2 could possibly work again if the multiplicity of that 0 is 2, right? So if it didn't work before, it can't work later. But if it did work before, it could work again because it has a higher multiplicity. Okay, so we might need to try negative 2 again. I think I'm going to do that just so that we can kind of try it out and see what happens. But let's do our possible rational zeros again. P would be divisors, and I'm just doing this because it's going to narrow down my list. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6 would be dividing that 6. Q would be divisors. This is sort of doing it for this guy. Divisors of 3 would be plus or minus 1 and plus or minus 3. So my possible rational zeros would be all of those over 1. And now putting them over 3. 1/3, 2/3, 3/3 would be 1, which we already have, and 6/3 would be 2, which we already have. So we were able to eliminate quite a few, right? I think above we had 18. Now we have 1, 2, 3, 4, 5, 6, so 12. So we were able to eliminate quite a few. We also know that 1 and -1 didn't work above, so we can eliminate those. But those are the only two we can eliminate because the -2 could work again. We're going to try, just because it could. All right, -2, and now we're looking at coefficients of 3, -4, -17, and 6. Because we're trying to now factor this guy. Bring that down, it's 3. Multiply, we get -6. Adding those is -10. Multiplying here, we get 20, which gives me 3. Multiply there, we get -6, and that's 0. So it did work a second time. That tells me that x equals 2 equals -2 is a 0 again. X plus 2 will be a factor of this guy, which means it's a factor again of the original function. So let me come up here, use a second column here. Now I'm going to say f of x will equal x times x plus 2 squared, because we're going to have another x plus 2. This guy right here, this 3x cubed minus 4x squared minus 17x plus 6, breaks down into x plus 2 times 3x squared minus 10x plus 3. Using the coefficients on left there, oops, that's a -10. On the bottom of the synthetic division. Okay, so this is my original function. So I'm just kind of breaking down everything step by step. Now I have a quadratic left. I have a couple of options here. I can try to factor that using our traditional techniques for factoring. I can try to continue this process. I can still use synthetic division on a quadratic. We just typically find that it's easier to not. I think this one actually factors. 3x and x gives me the 3x squared, and if I put a 3 here and a 1 here, both of them negative, I'm going to get my -10 because I get the -9 and the -1. So this is my f of x. I'm going to read my directions again to see what it asked me to do. Factor it into linear terms, which I did here. That's this. Those are all linear. And find the zeros. So the zeros are actually x equals 0 from that first factor. X equals -2. That one has multiplicity of 2. The next factor there will give me x equals 1/3, and the last one will give me x equals 3. So those are my zeros. Okay. Oops, wrong way. Can be a big process, you can see. This one I want to look at because it has something a little bit different. P is the divisors of -10 plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Q is the divisors of 1, the leading coefficient, so just plus or minus 1. So my possible irrational zeros are just the the p's, because when you put it over 1, you get those numbers, 1 or -1. Okay, so we have 8 possibilities. Let's try one. Try and skate through this as quickly as I can here. 1 comes down, multiply, add, multiply, add, 4, add, multiply. Oh yeah, check, that's good. That means x equals 1 is a 0 and x minus 1 is a factor. Notice here we're looking to just solve this polynomial, this polynomial equation. This question is actually a little bit different, but factoring it is what gets us to that solution, because if you have it in factors, linear factors, you can set those factors equal to 0. So we're kind of trying to accomplish the same goal as find the zeros, right? We could try 1 again. I don't think it's going to work just because I know what this looks like and I want to save us a little bit of time. So we're going to try -1. 1, -1, that would be -6. When we add there, we get 10. -10 gives us 0. Check. Very good. So notice here I just used the 1, the -5, the 4, and the 10. I don't want to reuse what I started with because, I guess I kind of skipped a little step here. My f of x, which started out as x to the 4th minus 6x cubed plus 9x squared plus 6x minus 10. After I factored out that x minus 1, I then had x cubed minus 5x squared plus 4x plus 10 left. And so I just wanted to work on that cubic function. So that's why I put those coefficients there. Then I found that synthetic division here, giving a remainder of 0, tells us x plus 1 is a factor. X minus the -1. X plus 1, and what's left is x squared minus 6x plus 10. That does not appear to factor. There are no two numbers that multiply to give me 10 that add up to -6. So 1 and 10, 2 and 5 are it. And even if they're negative, they're not going to add up to -6. So that doesn't factor. Remember, my ultimate goal is to solve this equal to 0, right? So that's going to give me x equals 1 from this first factor, x equals -1, but I also need to know where x squared minus 10x plus 10 is equal to 0. And I'm just going to use a quadratic formula on that since it doesn't factor. X equals opposite of b, which would be 6, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a is 1. 6 plus or minus, we have 36 minus 40. Ooh, that's -4. The reason I wanted to look at this one is because it is an interesting result here. We get the imaginary number 2i from that square root of -4. So x equals 3 plus or minus I. So these are my solutions here and here. We have 4 solutions there for this 4th power. I wanted to look at that one because the problem's worded a little bit differently, but also because we got those imaginary solutions. And that's okay. You can have imaginary solutions, you can have irrational numbers that have square roots that don't simplify, or you can have rational numbers. I think that's a good place to take a break. We'll come back to this application problem in the next video.